All right, so now we're going to talk about GLMs. That stands for Generalized Linear Models. And GLMs are extremely cool. There's so much to know about these things. There's so many extensions to generalized linear modeling, so many different kind of aspects of it. They're extremely flexible, can fit a whole bunch of different types of data, but we're not going to do most of that. That would be its own course that would probably be weeks, if not months long. We're going to take a very shallow dive into a very deep pool and just sort of talk about what you need to know for species distribution modeling. And this GLM, it's not used as much as some of the other methods, I think because it takes more work, but it's worth understanding if for no other reason than because it sort of forms the kind of basis of maximum entropy. So maxent with, to a kind of first approximation is GLM with built-in feature selection and a few little special extensions. And so it's worth understanding how this works, even if you don't plan on using GLM itself. And this is actually kind of common across sort of modern fancy machine learning and AI stuff, that often you will see things packaged as kind of a new method that, to a first approximation are just sort of GLM plus some extra flashy stuff, which is not, intended as a criticism of those methods, but it is to say that, underneath a lot of these new fancy methods, you'll find something that looks a lot like GLM kind of beating at the heart of it. Okay, so in species distribution modeling, the way we use GLMs, we typically use background, pseudo-absence, or absence points, as well as occurrence data. And this already sets it apart from BioClim and domain that we just talked about, because those methods, we actually just took our occurrence data and we basically drew a shape around our occurrence data in environment space. So those are climate envelope methods. They don't use background data at all, or absence or pseudo-absence data. So they're kind of fundamentally doing something different from what GLM is. GLM models are fit using maximum likelihood. I don't know that we're going to do a deep dive into likelihood, but I will put a tutorial in the GitHub repo so that you can learn a little bit about that if you're interested. GLM is, as I say, it's extremely flexible, but it requires a lot of hands-on work. I think in species distribution modeling, as with a lot of other fields, we kind of we have these tools that we rely on to do things for us, to figure out which predictor variables are important to our species, for instance, or what sorts of functions we should fit, things like that. GLM doesn't do any of that. It's very flexible, but you have to tell it what to do. And for that reason, GLM is something you should understand fairly deeply before you start to really use it for important stuff. Yeah, so hopefully what we'll cover over the next few minutes will give you at least an idea of the sorts of things you should be thinking about when you use a GLM. All right, so what we're kind of doing here is we're trying to contrast the places we've seen our species in environment space. So that's what these points are, with the places we haven't seen them. So what I've done here is I've plotted essentially the density or the frequency at which we observe different combinations of these environmental variables in our training region. So we've got in geographic space, we've got the training region that we say outlines the range of our species or something like that. And these colors here represent how frequently we see certain combinations of these two variables in that training region. So brighter areas represent combinations of environments we see a lot. Darker areas represent combinations of environments that we don't see, or combinations of environmental variables that we don't see very often. So this colored thing is essentially the distribution of the environments in our background. The points represent the occurrences of our species. And we're trying to infer a function that discriminates between the two. So a function that will tell us where we're more likely to see our species than expected, given the available distribution of environments. So how do we do that? The name generalized linear models might lead you to think that we're actually going to be fitting a linear model to some data, and like you're probably used to, so just straight up linear regression. So we have an x, we have a y, we fit a line that sort of explains the relationship between x and y, and then we have some error distribution, which linear regression assumes to be normal. So the differences between the predictions and the observations are assumed to be normally distributed, otherwise known as the residuals. So this is what a regular linear model looks like, but that's actually not very reasonable when you think about what our data is. Because our data, we don't have something ranging, some continuous variable ranging from 0 to 300 in this case. We have ones and zeros. We have presences and absences. And if you try to fit a linear model to predict presence and absence based on this environmental gradient, it's going to look really weird. First of all, it's going to be predicting negative, I don't know what a negative value even means. We're talking about 0, 1 data, presence, absence, but it's going to, your model is going to be predicting things below 0 and above 1, which is not what you want. It's the shape of this thing does not look like the shape of our data. That error distribution, it's assuming the errors are normal here, and they're so extremely not, right? So like this is a poor fit for our data, and the error distribution kind of makes no sense either. What we want to do is fit something like a logistic curve, where we say the probability of observing a 1, or probability of observing our species, is in this logistic function of our environmental gradient. So that's what we like to fit. And you notice this does not go below 0, it does not go above 1, and the error distribution looks a lot more reasonable. So this is what we like to fit, but obviously this equation here looks nothing like a regular linear model, which is like y equals mx plus b, or, y equals beta naught plus beta 1 x1 plus beta 2 x2, blah, blah, blah. But what we do with generalized linear modeling is we use this thing called a link function, where basically we say, okay, this is not something we can actually fit with a regular linear model, but z is, right? So what we can actually do is we can say, okay, y, probability y equals 1 is now this function, and this function is a function of this thing called z, but z is itself a linear model, right? So this is now like a multiple regression. We're saying that z is, there's an intercept value, and then it's a linear function of x1 and a linear function of x2 and x3, x4, and we add all those up, and that gives us z. And that allows us to fit a curve like this using a linear model, right? And so this x1 here would be one predictor variable, x2 would be another predictor variable, et cetera, et cetera, et cetera. So we're fitting a linear model here, but the actual prediction we're making is not shaped like a line. Basically, if we have 3 predictors, we're going to fit, say that the z is some linear function of those 3 predictors, and then it goes into that, what's called a link function, that's what this is. Yeah. It goes in that link function, and then we make a prediction from that. Yeah? And that's cool, because it allows us to do this sort of logistic regression, binomial regression, using linear response functions. But we don't have to use straight up linear response functions. We can actually control what these functions look like. And this is where GLM gets really flexible and really fun, because you can say, okay, maybe the response of my species to an environment isn't actually a straight up line. Maybe it's quadratic, right? Maybe I think there's a peak in how it responds to bio 11 here, I guess that is. Maybe I think there's a peak, and then it sort of goes downhill from there. Right? So you could actually fit quadratic functions or cubic or quartic or whatever you want to fit of each of these environmental variables. So you could actually make this linear, this one quadratic, and this one cubic. And at the end of the day, those are all used to essentially control how the suitability of habitat predicted responds to your environmental gradients. But at the end of the day, those all still go through the link function and make a 0-1 prediction, or a prediction of the probability of observing a 1. So you can play around with GLMs, and you can fit kind of a whole bunch of different functional types and use those to predict the probability of presence of your species. So you can go in predictor by predictor and tune those response functions until they seem biologically plausible and fit the data well and all that sort of stuff. It's very, very flexible, but again, it requires you to go in and actually tell it how to fit all this stuff. And that brings us to an interesting discussion point. Well, I mean, this is just a video, so we're not going to discuss it, but it's worth thinking about when might it be better to build your model with this level of manual intervention? When might you want to specify what those response functions look like and specify different response functions for different predictors and all that sort of stuff? That's really interesting to think about, and it's worth determining what sorts of questions you might be asking where you would want to actually have that level of control versus situations where you might actually want to let the algorithm tell you automatically what's important and what isn't. So think about when each of those approaches might be appropriate.